Hello everyone. Today we are going to be looking at the triangle inequality theorem and the hinge theorem. Now these two theorems are going to focus on the lengths of the sides in comparison with each other. So yesterday we kind of compared the sides and the angles to each other, and today what we're going to do is just look at the sides. Now the heart of our first theorem, the triangle inequality theorem, is very instinctual. In fact, it's something that you do probably weekly without much thinking about it. And this is where this comes into play. What the triangle inequality theorem essentially says is the length of one side of a triangle is going to be shorter than the combined length of two other sides. Now, if you think about this in terms of cutting the corners, that means that it's going to be shorter to go straight across here as opposed to walking around both the sides. And guys, we can see that at a glance. Yes, it's going to take longer to go around this way than it would to just cut the corner. And that's why we tend to cut corners so much. So you can see this is done two different times with this little tight corner here, going that shorter distance, or the further out corner over here, creating what we call a desired path, or where we wish the path would go. So many people walk down there that they make their own path. So you guys do this theorem daily, but we can also look at it in terms of the triangles that are used and even do some algebra with it. So let's take a look at that. What we're going to start with is setting up some formulas that we can use later on. So because the triangle inequality theorem tells us that the sum of the lengths of any two sides need to be greater than the length of the third side, that means we can actually set up three inequalities. I know that this side A is going to have to be smaller than the combined length of B and C. So that means that A is less than B plus C. We also know that if we focused on B would also have to be less than the combined length of the other two sides, A plus C. And last but not least, our third side, C, would have to be smaller in length than the combined distance of A plus B. So that means we're going to have these three inequalities to work with. And we can use that to figure out whether triangles we design will work even if we don't have the physically drawn triangle. And we can do this using this theorem, and you can also do this just by measuring things out. So let's take a look. So I'm asked if I can construct a triangle with the side lengths 9 centimeters, 6 centimeters, and 5 centimeters. Now, if this is true, I should be able to set up three inequalities with the sides that are all completely true. Can I say that 5 is going to be smaller than 6 plus 9, so one of the sides is smaller than the combined other sides? Well, yes, because 5 is smaller than 11. We could also say that then is 6 smaller than the combined length of the other two sides, 5 plus 9? And the answer is, of course, well, yes, because 6 is smaller than 5 plus 9, or 14. And, of course, check the final side, is 9 smaller than 6 plus 5? Well, again, the answer is yes, because 9 is smaller than 11. Now, what you might notice is there's no need to do all three of these. Really, since 9 is our largest side, it's automatically going to be larger than the other two. So I automatically know that this inequality will work for both my smaller sides. Like 9 will be bigger than the 5 side, and 9 will be bigger than the 6 side. The only one that might be problematic is if the other two sides, the two smaller sides, are not going to be large enough to be greater than that third side. So if you just look for your longest side and check that it's smaller than the combined length of the other two sides, you will be good to go. And if I were to take these, the other way to solve this, if you're like, oh, I can't do the algebra, is going to take some measuring. So I can actually physically take a side length that is 9 centimeters long, which is this one right here. I can take a side length of 6 centimeters long right here. And I can take that final one of 5, and I could just see, can I make a triangle with it? And the answer is, well, it might take some arranging, but yeah, I made a triangle where all of the ends touch, and it's clearly a triangle in shape. I can try the same thing with my next one. In fact, let's first try it with the segments. I have a segment of 9 centimeters, a segment of 5, and a segment of 4. And I want to see, will this form a triangle? Well, if I try to lay these out, my ends don't touch, so I'm going to try to bring it in a little bit further. And oh, guys, what I made here is not in fact a triangle, it's a straight line. Now I know this has some depth, so it's a little bit harder to see, but this is not actually a triangle shape when they're all forced together, right? So that means that this cannot form a triangle. And let's see what's going to happen to the algebra to show us that as well. So I didn't need to make all those side lengths. Again, what I'm going to do is I'm going to check the longest side compared to the 2 smaller sides. Is 9 larger than 5 plus 4? Or smaller than 5 plus 4? Because if it's smaller than 5 plus 4, that means this will make a triangle. Well, in this case, when I simplify it, I get 9 is smaller than 9. Well, that's not true, because 9 equals 9. So because the statement overall is false, that means that these cannot form a triangle. They will, in fact, form a straight line. You can also find instances where it's just impossible to make the triangle. So, for instance, looking at the algebra in this final one, I'm going to again look at my largest side compared to my 2 smallest. Is 9 smaller than 6 plus 2? Well, that's a resounding no, because 9 is not smaller than 8, or 6 plus 2. So since this is not true, this can't form a triangle. And I can show that again using the actual lengths if I would like. I have a length of 9, a length of 6, and a length of 2. And when I try to form a triangle, as I try to get these ends to meet up, notice how there's going to be that big gap. They can't actually touch each other while still touching the end of that longest segment. So that means that there's no way that these 3 segments could form a triangle. So that's one way that we can use the triangle inequality theorem. Let's check out another way to go about it. One thing that this theorem is particularly useful for is trying to figure out a possible range of lengths for the third side of a triangle. So triangles are used all the time in construction, and we're going to look at one example in just a moment. But a lot of times what we're not trying to find out is what an exact length is. We're trying to figure out what are 2 possible lengths, or what are a few possible lengths that we could do in a triangle and still make a valid triangle or a good build. And that's what problems like this help with. So what it's saying is, let's say that we have this length of 4.7 and we have this length of 6.8. How big could this final side be? And it could be a lot of different lengths, right? Depending on how much I open or close this in the angle that we choose for this. Now, let's find that range. And I'm going to call this range, let's just go with Z, just for fun. So that's going to be the length of that third side. Well, I know that Z is going to have to be smaller than the combined length of 4.7 and 6.9. I also know that 4.7 will have to be smaller than Z plus 6.9. So these 2 sides will have to be larger than the third side. And I know that 6.9 is going to be smaller than Z plus 4.7. So these are those 3 inequalities we found with our theorem. So all I need to do is use what I know about inequalities to solve for Z and get my range. We'll do this one at a time. So in our first inequality, all I have to do to get Z by itself is really just simplify this side of the equation. And that's going to give us Z is smaller than, or is less than, 4.7 plus 6.9, or 11.6. And this is, of course, centimeters. So I know that that's the absolute longest I can make Z. Like, it has to be a little bit smaller than 11.6, or I won't have a triangle. Now what I want to see is how if this is how big I can make z, what's the smallest value I could use for z? And that's going to be determined by one of these two inequalities. So let's simplify each of these two inequalities and see what happens. For the first one, we have 4.7 is less than z plus 6.9. Now I can solve this like I would in normal equation. I can move the 6.9 to the other side by subtracting both sides by 6.9. This is subtracting 6.9 from both sides. This is going to leave me with z on the right side, and on the left side, I'm going to have a negative number. And guys, I can tell you that number is, well, 4.7 minus 6.9 is going to give me a measure of negative 2.2. But essentially, it's just saying that z can't be negative. And since z is a distance, it's not negative anyways. So this is not a particularly helpful inequality. Let's check our final one then. Here, when I solve for z and subtract 4.7 from both sides, I find that z would have to be bigger than a positive 2.2. So I end up with another restriction on z. Z is going to have to be larger than 2.2, and it's going to have to be smaller than 11.6. So we put that range like this. You put the smaller number on the left, the larger number on the right. Don't forget we do have units here. And since you want z between those two, go ahead and stick z right in the middle. Those are the restrictions that we have for the measurements of our third side, or the measurements of z. You might notice that there's a bit of a shortcut. The only two inequalities that you really need to look at are the inequality formed by z is less than the two other sides, and the inequality formed by the second largest sides, the largest of the given sides, is less than or equal to the combination of z and the smaller side. The reason being, when you have this middle one here where you got the smaller given side, it's always going to end up giving you a negative number. And since z is talking about a distance, we don't actually need that negative number. It's not useful for practical things. So that means if you check these two, you will be good to go. One area in which we use those ranges of side length is really when we're helping design things, like I had said earlier. In particular, this is like a kitchen design. And the problem explains it a bit, but essentially, when you're designing a kitchen, you really want this work triangle to fit a few restrictions in terms of length. And essentially what they're saying is, in order for a kitchen to be easy to work with, you don't want the sum of the sides of the triangles between the key appliances, refrigerator, stove, and sink, to be greater than 20 feet. You also want the stove to the refrigerator to be the shortest of the lengths, and that's just because those two are most frequently used with each other. There are some other restrictions that they have. They really don't like the distance between the sink and the stove to be less than 4 feet, but that's a more minor note, and we won't worry about that right now. Essentially, what this question is going to ask is, even without drawing your full kitchen blueprint, which can take some time, would these distances actually work for a work triangle? And you can check that pretty easily. So let's say I had a stove to refrigerator of 5 feet, a refrigerator to the sink of 7 feet, and a stove to sink of 6. So these three distances will make the three sides of the triangle. And I'll just quick add them in. And first off, I should make sure that this actually makes a triangle before I assume that this is going to work for a work triangle. And I can do that, of course, by just checking if the longest side is shorter than the two other sides added together. And sure enough, it is. So good news, I've made a triangle. That's excellent. Next thing I should check is the stove to refrigerator the shortest length? Yes, it is. It's the shortest of the three given, so that's another restriction met. And does the total length of the sides exceed 20? Well, 5 plus 7 is 12. 12 plus 6 is 18. So since overall I've got 18 feet of length in my triangle, it does meet my restrictions of that 20-foot max. So that means that this one right here would make for a good work triangle. And I can check the second one as well, and I'll find that no, it does not make a good triangle, because even though this one is the shortest, and the sum of these is less than 20, 6 plus 4 would be 10. So